So thank you for coming, everyone. Thank you for having me. Today I'm going to talk a little bit about some recent work that I've been doing, sort of a data assimilation project of sorts. The main goal for the project is to blend measurements, observations with a physics-based model, and do that in a somewhat intelligent way. I'll stress somewhat, but and also identify some of the obstacles that we've been encountering along the way that have been kind of keeping us from making much progress in terms of data assimilation with a physics-based model. So, in general, the motivation for embarking on this work has been to try to replace the operational models that we use, the most of the time very empirically based models that we use, because they are limited in terms of their predictive capabilities. And we see that physics-based models offer a pretty good potential for prediction if we can overcome, a few, many, I would say, obstacles. So this is kind of a start toward along that path. So this is kind of a setup of the premise of this work. A lot of data assimilation in the lower atmosphere, in the troposphere. Basically, the name of the game is to get the initial conditions just right, to tune the initial conditions and let the internal physics of the model propagate on. So in terms of the lower atmosphere, and actually, let me use the mouse here if I can find it. The lower atmosphere model here is in very general terms more of a kind of a chaotic system where if you have kind of an initial two model states and you propagate those forward in time, after some amount of time the subtle differences will kind of add up and the two states will kind of diverge. On the other hand, up in the ionosphere and thermosphere, we're more in the kind of strongly driven regime. And that means that if you have two initial states that are vastly different, but you apply the same forcing to those as time goes along, these two initial states will sort of converge in a similar form. So that's very general terms to describe the premise, but that's kind of the starting point here. And I should mention here there's a paper by Stefan and others, Codrescu and others from last year that really sets up that argument really well, I think. So what do I mean by that forcing term? In very broad terms, I'm talking about the solar wind, the solar irradiance, upward propagating waves and tides. This is a very broad overview of the system where very complex systems are replaced with dotted lines. But that kind of gives you an overview of what I'm looking at. I'm going to be emphasizing more today the irradiance part and the solar wind, magnetosphere, ionosphere, thermosphere interactions, more so than the upward propagating waves and tides, although those are absolutely important as well. So here's a little example of those two influences, the solar wind and the solar radiance. We're looking at right in the middle of the October, November Halloween storms from 2003, and there's this slight lull in geomagnetic activity right where the red line is there in the upper plot, and you see a global map there of thermospheric neutral densities. And what you can see is even in this lull, things have kind of recovered a little bit, and you're seeing enhanced densities near the subsolar point in the early afternoon, and you can clearly see the diurnal day-to-night differences and all that. As we step through and we go into this second period of strongly southward turning BZ, the geomagnetic activity ramps up very quickly, and this background is completely obliterated by the heat coming in at higher latitudes, and you see a whole spectrum of waves traveling from high latitude to low latitudes, and you can almost see near the end of this period here where things are almost starting to recover again. The kind of picture that you saw about a day prior is kind of reestablishing itself. So that's just a kind of an example. I'll get to the lower chart, and I'll revisit the lower chart here in a couple of slides. So this is a redo of that slide from 2 slides ago. But now I'm talking about how we might go about modeling the system using a physics-based ionosphere thermosphere model. I've replaced the dotted lines now by a couple of parameterization models. So the top lines are capturing geomagnetic activity. The bottom line there is capturing solar irradiance, and we're doing that through proxies, the KP for geomagnetic activity. Sure, yeah. Is there a question? Oh, sorry. And the F107 radial solar flux proxy for solar EUV, FUV, XUV, anything that's absorbed in the thermosphere and ionosphere. So when we do this, because the proxies are not exactly accurate and they don't exactly tell us the information we need to know about how the upper atmosphere is heating, where it's heating, etc., there's a lot of uncertainty that builds up in these parameterization models. So one of the things that I've tried to do in this work is to essentially calibrate those boxes in a very simple way, but in kind of a real-time way, using in situ and remote sensing measurements based in the thermosphere. So that's kind of I would say, kind of a new twist on an old method there. So this is kind of the cartoon version of how that goes. If you, for instance, have an initial guess, would be the green curve. So this is your model, your background model with nothing done to it. The wiggles there, I'm looking at. I've run a Ford model and I'm recreating the neutral density along a satellite orbit. So you're seeing kind of these 90-minute or so fluctuations in neutral density. And then you might have, as the red curve shows, some limited observations. So there's a couple orbits there of neutral density observations. And so to get your model to line up with that, you could imagine solving a least squares minimization problem using variations of your model run, using slightly different inputs for F107 for KP, juggling that all around until you minimize the problem and get a solution, an estimation for those parameters. This is typically done. Something similar is typically done using an ensemble Kalman filter. And the part that I would put forward as being important is that once you estimate those parameters, it's important to let your model respond to it. So after these parameters have been estimated, I go back a certain amount of time and rerun the model. And you can see there, the blue curve now is that process. The blue curve, you can see, takes a number of hours to come into equilibrium with those estimated parameters, in the order of 12 hours to a day or so. But doing this, you can forecast forward past the current time, and you've kind of calibrated your model going forward. So, and again, if now in this forecast window you're stepping forward, you have new data that comes in, you're able to redo this process and capture any abrupt changes very well using this kind of a process. So TIGCM is the model that I've used. I suspect there's several in the room that are familiar with that model. I probably don't need to spend too much time on this chart, but I will say that it's a very good model in that it's not a sun to mud model. It's cut off at about 100 kilometers, right around the mesopause. And there's a variety of inputs that can be used. I've used some of the simplest ones here, and then tried to tune those. So, and now on the other hand, what thermospheric observations do I have to drive this with? I mentioned at the beginning that this is a very sparsely observed system. So this is how thermospheric models have been driven. I should say assimilative models have been driven in the past using ground-based radar tracking of satellite assets. This is how the U.S. Air Force does it. But there are also dedicated missions. We're going to have gold data coming pretty soon. Those are going to be very useful. I've used here in the next slides that you'll see, I've used accelerometer inferred neutral densities from Champ and Grace satellites, and we're going to have in the next couple of months, we'll have follow-ons to some of those missions as well available. There are also upcoming signals of opportunity from constellations of small satellites that we're working with as well. I won't go into too much depth here, but I think that's something that's kind of exciting, especially on kind of the civil side of things. The ground-based radar tracking is very difficult to get your hands on if you're not part of the DoD. So, but anyway, so here's what this process looks like. This is actually just the free run of TIGCM over most of 2003. The top plot is an orbital average of the Champ neutral densities in blue, and in yellow the TIGCM output. So you can see there it's reasonably good over the course of the year, but there are ups and downs, and those are kind of the things that I'm trying to get rid of. So on the bottom plot, you've got all the data, no averages taken here, and you can see this is a ratio of the model output to the data. So you can see, again, this is 2003. So the Halloween storms are starting right around day 300 there, and there's several very strong solar rotations there that really disrupt the accuracy of the model with respect to the data that we're looking at. So if I implement a scheme similar to what I've described here, estimating a correction to the solar irradiance and a correction to the geomagnetic indices, this is what it looks like. And so the larger scale residuals are for the most part removed. We go from, I believe it was 20-some% RMS error to about 3 or 4% RMS error in terms of the orbital average stuff, and even along the orbit, what you're seeing in the bottom plot, a lot of the strong solar rotational signals there are very well removed. So this is of course compared with the data that I've just ingested. So if we want to compare with the somewhat independent data source, I can use a different set of satellites, and that's shown here, which is the GRACE satellites. So basically the same thing, accelerometer inferred densities. And this is the data assimilation run. So, and one of the things that you'll notice, especially on the bottom plot here, is that there are some odd signatures in the data in the comparison along the orbit. And if I just kind of switch between the last plot and this plot, you see they're similar, but they happen they occur at different times of the year. It actually turns out that if you bin these residuals, these model residuals, in a latitude by local time frame, they're very persistent. So having sort of isolated what I consider to be kind of the internal model, not, I guess, errors or discrepancies with data, you can really get a pretty clean picture of what's going on, and it kind of boils down to a discrepancy in the day-to-night or diurnal amplitude of densities within the model relative to the data that we're looking at. And so the left plot there is for the ingested data. The right plot is for the independent validation data. But when you bin them this way, they look fairly similar. Amplitudes are a little bit different, but
can I get a clarification on what
yeah,
you're doing here?
Sure.
So you're using CHAMP you're assimilating CHAMP into TiGCM to steer its solution.
Right.
That would be a better prediction of what CHAMP would see. Then you're using the TiGCM inferred or calculated density along the GRACE orbit, and then these are the residuals that you get between TiGCM and what GRACE predicts. Is that?
Yes, that's right. The one on the plot on the right is what you described. The plot on the left is the residuals, the kind of the mean residual, using the CHAMP data itself. Okay. So it's essentially you've adjusted the drivers, but that can only get you so far. What are you left with at this point? And this is what you're left with. So I can't adjust these distributions out of the model solely by adjusting the F107 or KP inputs. Yeah.
So the difference, the CHAMP is at 400 kilometers.
That's right. It's about 400.
GRACE is
yeah.
500.
That's right.
So I'm wondering if we scale the GRACE density from 500 to 400.
Would you see a similar amplitude there?
Similar.
It could be. Yeah, I haven't tried that, but yeah, I suspect it would be. Yeah, those amplitudes tend to grow with altitude. Yeah. Yeah. So one of the things that we're starting to look into here is what internally to the model, what factors have a sensitivity, or I should say. What factors can I adjust within the model that would get rid of this? And so we're looking into various things. For instance, the viscous and ion drag terms that Vicky Xu has looked at in the last couple of years. Also looking at the specification of tidal and gravity wave signatures. And for that, we would probably have to invoke other modeling frameworks such as TimeGCM and even WACMX. But so those are the things that we're looking into going forward, just to see if there are errors that we can isolate using this technique and potentially find the sensitivities.
Just so I get the sign right.
Yeah.
The model's too hot or?
Oh yes, the model.
The
model is too low during the day and a little bit high at night. So the model's diurnal amplitude is smaller than that of the data.
There's a phase shift too.
That's right. Yeah. yeah, and it's somewhat latitude dependent as well. And these are binned, but the data that goes into a certain bin is mixed throughout the season and other factors. So it's an average. And so here we're back to this example of the 2003 storm. As we're going into it, you can see. Let me back up here once. Let me start this over. You can see at first you've got pretty good agreement with the data assimilative model in the bottom plot, and as you go into the storm, a lot of the features are reconstructed fairly well. The amplitudes aren't always correct, which we're checking into that, and of course model resolution has a lot to do with that. The forcing that you're imposing in the model has a lot to do with that. But so if we stay kind of focused on the Halloween 2003 events, here is all the CHAMP on the left and GRACE on the right density data in a latitude by day of year plot. And I've broken out, you can see I've broken out the ascending and the descending parts of the orbit so that they're not mixed together. They're just stacked right on top of each other. This is what the free run of TIGCM shows. So the main thing here is that there's a kind of a longer term scaling factor almost, you could imagine. If you get rid of that, you'd be doing pretty well. And that's essentially what happens when you do this data assimilative method. But another thing that's also interesting here, though, is you actually are catching some of the dynamics of the storm. When the activity comes, you're within some bounds of timing accuracy. You are kind of capturing the timing of some of these waves that are traveling through the atmosphere. You can see some of these here. They show up as kind of diagonal streaks, and these would be the traveling atmospheric disturbances that are caused by by these large disturbances. And if you zoom in very closely, the timing is not right on, because that's just kind of a constraint of our modeling technique. But that they're seen and are somewhat similar, I think that's interesting. One of the things that does not show up in the bottom plots is the signature that I've just circled here, which is the impact of the solar flare that preceded the geomagnetic storming. Just due to how the time scales that we're estimating the solar flux driving over, we're not able to capture something that small. But let's see. So I've mentioned that we're estimating the drivers, the solar drivers, such as F10.7, such as KP. So the question comes up: what do they look like? Are they close to the actual proxies? Are they wildly different? And they are for the most part on par with the observations. There are some important differences, and in fact, you want those important differences because your model would not improve without having some significant differences. But one of the things, one of the issues here, I should say, is that when we estimate solar flux and KP simultaneously, it's very difficult to disentangle which effect is coming from what, and this all relies on the information that you're pulling out of the neutral densities. So I'll show some discussion on that in a second. But so a lot of the spikes here that we see in the estimation and in the red curve here, I think a lot of those are actually, I would associate those or attribute those to quick spiky-like changes in, for instance, KP, and that's if you zoom in on those, you can really tell that you're soaking up some of the KP in the F107 estimation, which is not great. But another thing that we see a lot in the bottom plot here in the KP index is that it bottoms out a lot. And my first order guess on that is that the cooling, and I've zoomed in a little bit on that and looked, to see where is that happening, and it seems to be happening right after there's some kind of a disturbance in KP. As the thermosphere is recovering, that's when the estimated value tends to drop off all the way to zero a lot of times. And so one of the things that I'll begin investigating as well is how the NO cooling factors into that. Is that what's happening? Is there something that's not cooling off the model as quickly as the data would say it should be cooling off? So I can also kind of remove those lower boundaries by taking an upper envelope, kind of running, kind of like a running mean, only I'm taking a running maximum of the estimated KP. And if you look at that, if you stare at that for a long time, it's actually fairly well correlated. So there's some information there. But again, these are issues that I'll continue to look into. So let me back up real fast here. One of the questions I have is are there any ways to disentangle these two effects in the estimation process? And the answer that I've come up with is, well, neutral density is not that great at helping me to disentangle those two. And I ran kind of just a simple example study to show what density looks like if I all of a sudden I switch on F107 and ramp it up versus what it looks like if I ramp up KP very quickly. And so this is kind of the steady state solution that you come up with. This is a percent increase in the model density, depending on whether you are increasing solar flux on the left or increasing geomagnetic activity on the right. And they look fairly similar. There's some important timing differences. Densities tend to spike faster at higher latitudes for the KP step function, and vice versa for the solar irradiance step function. But in general, there's a lot of similarities there, so that it really doesn't help you much. On the other hand, we have other observations, such as composition or the O to N2 ratio, that have a huge contrast in how they respond to these two drivers. Now you'll see that this is similar to, like, for instance, the GUVI or the GOLD measurements, where we're looking at a column integrated ratio for O to N2 here, and then on the left, you're seeing that as the solar flux increases near the subsolar point, you have N2 increasing at lower latitudes, and on the right, when KP spikes or ramps up rather, what you see is you have all the energy coming into the poles. You have a disturbed circulation that is then kind of fighting with the normal solar EUV induced circulation. So at the high latitudes, you have upwelling. You have the heavier species like N2 coming up and being more abundant there. At the same time, you have the lighter species diverging away from those areas and converging on the equatorial latitudes. So you see that O2 is increasing in the equatorial region and N2 is decreasing there. So you have these two starkly different signatures. So going forward, this is one thing I really want to add to kind of the repertoire here is to be able to take in these types of data and work with that sensitivity. So here's what this looks like, kind of on a global scale here. This is again the Halloween storm example that I've been using. And now we're looking, instead of densities, we're looking at O to N2 ratios. And again, this is the column integrated value here. So as we step through this storm, you can see that the O gets pushed equatorward, and N2 is populating the higher latitudes, and this of course evolves around and is transported around as the Earth rotates, etc. So,
what height is that?
Say that again.
What height?
This is the integrated quantity. So it's integrated down to a fixed column depth of N2, and I think that corresponds to about 120 kilometers or something. A little higher than 100.
10 to the 19th column, about 130, 140.
130. Okay, yeah. So it is this integrated picture along a pretty big range of heights.
People always ask, well, what is this O to N2 thing?
Yeah.
I always say, it's the thing that Goovy measures.
We got to change that now. It's the thing that gold measures.
That literally is what it is.
You're right.
It's what you see
Yeah.
when you look down at the atmosphere and the ultraviolet.
Yeah.
I'm changing my story now. What I'm going to say in the future is, it's that thing that gold measures.
Right. Yeah. So I mean, at the same time, though, it's very well correlated with the in situ O to N2 ratio that you would see, for instance, at a given height, and maybe at a given pressure level, or maybe it's better correlated with one or the other of those. I'm not sure.
And it's indicative of vertical motions.
Absolutely, yeah.
In the thermosphere. So
Yep.
you just see how there might be a circulation
Mhm.
pattern behind that storm time.
Absolutely. Yeah. So this is these are Goovy measurements over a similar time period here, a couple days, and you can see they're stacking up every orbit. You can see them, and so the top is what was measured by timed Goovy, O to N2, and this second plot there is the free run of TIGCM, and the third plot there on the bottom there is what comes out of the data assimilation run. So I have only ingested the accelerometer measurements, so I wouldn't expect to have a huge change in the behavior between the middle and the lower plot. I guess, or I should say, any differences there are somewhat accidental, and they do look fairly similar. So I think there's some definitely interesting things to look into there. Certainly, the asymmetry between heating between hemispheres is going to have an effect on how these look in the model, as well as just the timing of when the heating occurs. So these are all kind of interesting things to look into, and I think this technique, more than just a kind of a data assimilative operational capability, it can also help to isolate various things from the drivers, from the huge effect that the drivers have. So. And yeah, I think that's all I've got. So I'll just leave my summary up and take any questions.
Plenty of time.
Yeah, I have a couple of questions. One concerns the choice of the backward time history. How far back you go? Is there something that determines an optimal choice for that?
Not exactly. I ran a lot of studies, just short little example runs, similar to these runs that I've done, and I've looked at in very general terms, the timescales of response, and so I've come up with kind of a rule of thumb that a day works well. But that's not to say that I couldn't shorten that, and that wouldn't work very well also.
Okay, now, thank you. A related question on how to optimize. So, optimizing these two parameters, F10.7 and KP, based on CHAMP, sort of long track CHAMP data, which is a relatively simple parameter, but and maybe because it's just that one track that the GRACE is not doing as well as it might, and it kind of raises the question, and I'm wondering if you've thought about how to do this. But suppose you want to assimilate more globally or more multivariate types of data. What's the optimization path for doing that in this the mode that you're using here?
Yeah, it's something I'm working on, and I don't have the answer to it yet. Certainly, I'm going to be using some of the GPS-enabled CubeSat constellations to drive this, as opposed to a single accelerometer measurement. So in terms of assimilating many different satellites, potentially at different orbits and altitudes, that's something I will be looking into. I don't think that will be too much trouble, but when you get into the multivariate world where I'm trying to assimilate gold and mass densities, there's just going to be some tuning that will have to be done in terms of weighting one versus the other. And at this point, trial and error is all I can do. It gets really computationally intensive to actually try to optimize this. Yeah.
So these KP and F10 are quite global indices, and you're seeing a lot of structure, diurnal things that are missing, and presumably that's inside the physics of the model.
Right.
And so tweaking with F10 on a daily basis isn't really going to address the subtleties of that model. How do you, while you were talking, I was trying to come up with ways in which you could either have a local nudge, spatially resolved nudge of some parameter, or a non-uniform F10. So, the F10 in this part of the world gets bigger
Right, yeah.
than the F10 in this part of the world, so that you can start to try and address some of the local, until you start assimilating local data and coming up with a way to tune the local element of the model. Trying to do it from a global perspective seems like it's missing a very key component.
Yeah, I think you're right. A key component, especially for some of the ionospheric applications, right? For satellite drag, the getting the orbit average right is pretty good. But I've taken the approach of doing some of the internal model tuning or just assessing offline. So we're looking into that right now. I've got a study going that we're gonna rerun this using different models for the viscous and drag forces, and that really controls this day to night circulation and therefore the day to night difference in temperature, and as well as some other key features here. So yeah, more in an offline setting. Once we've kind of more or less isolated the solar and geomagnetic driving, then taking a look at the internal workings.
I'd argue from those figures that the major discrepancies are global scale or synoptic scale. Certainly there's some smaller scale stuff, but it's relatively, it seems relatively slight compared to this offset, and it points squarely at this diurnal variation discrepancy, which we've been
which we talked about many times in the past.
And what I'm noticing in this figure in particular is as I mentioned before, in addition to, it's not just, if I'm reading the figure right, it's not just a day-night thing. It's
Mhm.
There's also there's also a phase shift, and so that maybe suggests some clues in how to get a better a better background physics that would tune that out of there and then have less offsets
Going into the
in
process.
what you were
Yeah.
trying to fit. I'd also think that, I mean, the global scale stuff is got to be predominantly solar. The I'll say synoptic scale stuff is probably geomagnetic.
Could get tides.
Only way to, yes, but the only way to improve the mesoscale, let's say, stuff on a physical basis is to be able to capture that variability with a more comprehensive atmosphere.
Right. Right.
All right, somebody not on that row.
Yes, I was wondering about this. So this systematic day-night difference, you cannot reduce this by just because you are adjusting f10.7. If you just increase the f10.7, at least you will. Intuitively, you will think that will
It's not
increase
really
the daily bias, the small.
That's true. Yeah, you probably, if you scaled up the f10.7,
Yeah.
you would have a larger diurnal amplitude. You're right.
Expected to.
I guess my comments, I should refine those and say, if you're trying to also minimize the bias, you can't do it that way. The bias between the model and the and the observations. So yeah, if I thought the observations were, for instance, biased low, I could scale them up a little bit, and maybe some of this might go away. That's another thing just to test, kind of an easy thing to test. Yeah.
All right, Tom.
You'll like it. It's a solar question. Solar-oriented question. Looking to the future of these more sophisticated models like WAC-MX or WAM, do they also rely on f10.7? And if so, why? Because we have the UV solar spectrum to great detail, which we can give in near real time, at least as long as STO and things like that are up. So is there any future paths to that? More detailed.
I think there could be. I mean, yeah, I'd say typically yes. Most of those models rely on what we call the stand bands. I think.
Well, no, but they can be driven by. I mean, we have the option in all of our models now for FISM,
Right.
which
Right.
is based on measurements.
Mhm.
It's still a digestion of measurements.
FISM is a module or something?
No,
It's Phil Chamberlain's solar model. It's based on measurements by C and SDO and others, and we've run directly off of measurements. But of course, it's nice to have a system that gets you through the gaps and all that, so you have a continuous record. And FISM does that fairly well. And there's plenty of other options. We have a large body of work that Liang has led, running off of other direct solar measurements. The thing is, as you're noticing, well, in your approach, you're gonna normalize that to the CHAMP data anyway.
Right.
But
But I would say what I would want to do though is have some kind of a solar input that captures
the
a
spectral
lot of
variation,
the exactly,
and the day
and
to day,
and then
the
do
flares.
exactly.
The F in FISM stands for flare.
Right.
So it includes all the flares and all the spectral variations and all that stuff, and it's much higher cadence.
Mhm.
And so something like that is a more powerful tool. And that's why we have those those options, but you can't just put in any old solar measurement because there's always these discrepancies and offsets. And I remember a talk a student that Tim Fullerell's gave solar reading a couple years ago. He said, "Oh yeah, well we put the new solar measurements in, and of course and everything got worse." And I showed it to Tim. He said, "Well, of course, I mean it's model's tuned for what we use.
Yeah.
You can't just change.
Yeah, there are
Can't just change the sun."
a lot of obstacles to moving to that. I
It's
think it
the
would
sun
be.
that's the problem, not the model.
It is, because we don't know how bright the sun is. There's still, 10, 20, 30% error bars in much of the solar spectrum. Mostly absolute offsets as opposed to.
Right. And so I would imagine, a technique like this or something similar could be used instead of taking an F-10.7 and estimating that out of thin air. Take the measurements, the best measurements that we have, cobble those together into the spectrum that you want to use to drive the model, and then potentially calibrate different parts of that spectrum over longer time scales, hopefully find the persistent scaling that works best.
The big problem with F-10.7 is that there are periods of time when it doesn't, when its relationship to the actual EUV is different than it normally is,
Yeah.
particularly at solar max and solar min. And so, and day to day as well, or
when
rotation
it's
to rotation as well.
exactly when it's flaring all the time around day 300 there, it's doing things that EUV are not doing.
It'd be interesting
So.
to compare this to the C measurements for
Right.
the same period of time.
Yeah.
All right, any other questions, comments?
What is the advantage of IRIDA over the ensemble Kanban?
The difference, the main difference is with an ensemble Kalman filter, if you're estimating drivers, which kind of need to be doing, you're estimating those and then you're moving forward in time. And when you do that, your model is not catching up with what you've just estimated. So if there's a lot of, and then that tends to work for quiet periods, but when there's a lot of variability in for instance, KP or something like that, your model is constantly going to be trying to catch up with what you're estimated, and it's always going to be about 12 hours behind. So it's kind of a filter convergence issue.
How many ensemble do you want?
For this, 9 or 10, something like 9 or 10. So it's a lot less than a typical ensemble Kalman filter of 70 or 90 or so members. But the other side of that coin is that I have to go back and rerun them several times to get the convergence. So it actually about evens out to the same computational burden as an ensemble Kalman filter.
So what is the KP range and the F10.7, 10.7 range you're using from all the way from solar min to solar maximum?
So for KP 0 to 9, and for solar, I think I capped it at I don't know, 50 or something, very low and very high, just to make sure nothing crazy was going on. But I never ran into those boundaries, at least during this year. So I don't quite run in an ensemble, so I don't have to have a model running at the upper boundary and the lower boundary to catch the whole range. I just run variations of the model. So.
When you tested your model by doing the step function increase in case of P, how did you suppress the high frequency ringing due to that?
So let's see. Now, are you referring to
The step function increase in case of right there.
these ones?
Yeah.
No, these were offline, so I didn't do any data assimilation with these. So you will see all of that, and this is just a snapshot, maybe 1 day later, kind of the more or less equilibrium state after about a day.
mean, this is realistic. I mean, the sun and the magnetosphere do this to us all the time.
Right.
Yeah.
And the atmosphere figures it out.
Right.
And the model figures it out.
Yep.
Because the thermosphere or ionosphere system absorb all that energy and kind
Yeah.
of smooth it forward.
So I mean, if let's see if I can.
Yeah,
All kinds of excitement.
yeah. The thermosphere, it's like, well, you get hit by flares all the time. The
Yeah,
atmosphere
and-
shrugs it off.
Yeah, and so all of that ringing is captured in this lower model, but again, it's the inputs are kind of calibrated to best fit the data, and the ringing and all of that doesn't harm you. It's actually capturing some of what the observations are seeing, although it's usually offset in time by some factor. But
PIDs and stuff.
yeah.
Currently, you only perturb the solar forcing. How about the lower atmosphere forcing? In TiGCM dart, we sometimes need to perturb the electro fields. I mean, around the low boundary. So, what's your idea about this?
Yeah. So my idea going forward is to leverage some of the work that's already been done. For instance, some of the work that Nick Petitella has done with WAC-MX, or some of the work that they've done coupling WAM IP to the lower atmosphere models to capture that variability there. And of course there may still be some residual scaling that has to be done, but that would be how I would capture that kind of variability in this kind of a modeling framework, is to transition over to that type of a whole atmosphere model.
Anybody else?